hello everyone. We're going to talk a little bit about some of these concepts that Michael always so aptly sets up, which is fair data. We're going to talk a little bit about fair data, what this means. We're going to talk a little bit about data catalogs, namely how can you actually use fair data. And then I'm going to talk a little bit about what we mean by foundations of AI, because I believe that AI is becoming quite a buzzword, but a lot of people, if you really ask them what they mean by AI, it's usually nothing more than advanced statistics. So we see AI as something much different. It's not repurposed neural networks, or oftentimes something even more lightweight. I've seen people talk about Python scripting as being some form of AI. So who are we first? So I'm the Chief Data Officer for Ostus. Ostus is a German headquartered company in Aachen. We have around 150 people now globally. I have helped set up the US headquarters that we have in sunny Melbourne, Florida, where I live most of the time when I'm not here traveling around Europe, which is actually quite a lot of the time nowadays. And then we have a development team in Dalian, China, and we have another development team in Chennai, India now that helps to do a lot of our coding. So we pretty much run in a 24/7 environment now, which is very interesting, and it's challenging and exciting at the same time. So we're seeing a lot of growth in the space. And in fact, also now, as you'll see with what I'm going to talk about at the end, we're even starting to move beyond the pharma space. So FAIR, right? Everyone sees this logo, everyone hears about this term, and it stands for making your data findable, accessible, interoperable, and reusable. So if you can't find your data, good luck running TensorFlow on it. Good luck doing anything with it. If you can maybe find the data, but you can't actually access it, again, good luck trying to do analytics or trying to do anything with the data. Once you can find data, once you can access data, the real key, everyone wants to automatically jump to reuse. I have a lot of customers that tell me they think that the big advantage of going FAIR is the reusable part. It's actually, though, the hard part is the interoperable part. This is where you really have to take care in things like your data dictionaries, the terminologies you have, the models that you build, how you connect things together. If you do a good job at that, and if you layer your semantics correctly, actually the reusability comes pretty much for free, right? Because you can repurpose semantic models, you can repurpose schemas, you can look at data from different perspectives. You can even have software that, for example, will give you perspectival workspaces, right? So now the receptor could be looked at by both the chemist and the biologist. Right? It's the same data, it's a receptor. One cares, can I excite it? The other cares, what does it do after it's been excited? What are some of the upgrade or downgrade patterns? How does it affect the cell next to it? What happens over the long term? But it's the same item that we're looking at, but two very different perspectives. So FAIR is really picking up some steam, so much so that recently this paper appeared in Drug Discovery Today. This was sponsored by the Pistoia Group. I'm a member of this publication. Basically, we had 18 authors on this paper, which is quite impressive, I thought. And the pharma participants that were on there included Bayer, Novartis, Roche, MSD, AbbVie, and AstraZeneca. So as you can see, a lot of the people who are interested in this type of space played a role in this. And so this paper helps to define some of the underlying features of what we mean by FAIR. But I want to talk about FAIR a little bit differently. I want to take you on a very pragmatic approach to FAIR. And what I mean by that is, even if you read our paper in Drug Discovery Today, you'll often hear people talk a lot about FAIR in terms of sharing information, in terms of open source, in terms of using academic data. But instead, what I want you to think about with FAIR is I want you to think about the Internet of Things for a minute. So this is the shift. When Michael talks about digital transformation versus optimization, I want to challenge you with a new way of thinking about your data. So to make your data fair, think of your data sources now like these intelligent things we have in our houses. So the coffee machine, the television, the dishwasher. What do these things do nowadays? Well, what they're able to do is they're able to report a little bit about themselves. They're able to say, hey, I need my maintenance done. Or I have connectivity to the following network, right? Or it can tell you a lot of information about the use, right? So it can, smart lights can go on and off in your house. Smart thermostats raise and lower temperature and things based on the patterns of you coming home from work, or it can sense from your smart car that you're already on the way, and so then it starts your air conditioning or something, or your heat. So if you think about your data this way, though, then what happens is all of your data in all of your silos starts to become a bit self-aware. And what you need to think about with your data now is, instead of thinking about all of this massive integration, think instead about the optimization of these kinds of data sources. So instead of thinking about building the next big platform, the next big storage device, the next big data lake, the next big data warehouse that's never finished, instead, what I challenge you to think about is think about leaving your data where it is, making your data locally smart. It says, hey, I'm an Oracle database. I'm in 5. Whatever. I contain patient data. Hi, I'm a SQL database. I contain chemistry data. I contain bio data, and so on and so on and so on. This is the technology that we're working on. And if you go read Gartner, Forrester, PricewaterhouseCoopers, and even talk with Google, you'll find that virtualization and federation is the future. So we're moving away now with technology from this idea of putting everything together all the time. So what's happening is a lot of companies are pumping their data, terabytes of it, into a data lake, right? I had one customer tell me, we have 6 terabytes in a multi-node cluster in our data lake. And I said, really? Wow, incredible. So who uses it? Well, no one yet, right? So no one's using it, but it's there, right? So they built this technology, and now they said, well, the problem is we have to hire a whole bunch of data scientists now to actually go through and figure out what's in there, and then figure out how it goes together so we can start putting these analytics on top of it. That's a huge task. Those people are hard to find, and they're expensive even if you can find them. And it's going to take you maybe a year to clean data and maybe a year or 2 to do all of this integration. You've not run an analytic yet. People will start to run out of patience. So what I'm going to talk about is this type of a framework instead. So data catalogs. Basically, what you have with the data catalog is you have the normal consumers and producers. So a data producer can be a data source of any kind, and what it does is it basically publishes up its metadata. So like an Internet of Things device says, I'm on or I'm running, or I'm empty or I'm full, or I need maintenance or whatever, what it does is it says, this is what I'm about. Here are my column headers. Here are my table names. Here's what's in my file store, okay? So it publishes that metadata up into a catalog, and the catalog is the thing that can be used then to search semantically and pull the information out of that data. Okay, so the consumer can either go directly to the data producer, the consumer can either talk directly to the data source if they want, or what often happens is you use search to go through the data catalog. So what you do is you start to describe at least a very small amount of what's all inside of these different data sources and where they live and how you get to them. So now when someone says, I want to find all the patient studies on a specific kind of eye cancer, and I want them in a certain age range, and I want them from a certain area, but I don't want people who had chronic kidney disease or something like this, right? You need to know where that patient data is. You need to know where your oncology data is. You need to know where your diabetes data is. You need to know a whole bunch of things there. The catalog is your portal, and what happens with the catalog is you are able then to have reference master data and mappings between the producers and the catalogs, okay? So this is part of this findability, accessibility piece, right? The reference, and the reason I'm calling it reference master data is because it's a type of very important data in your company, like any other kind of master data, but it's about the data. It refers to things. It's not just about the labels. It's actually the real problem of reference, philosophically, from Frege. Right? You point up and say morning star, evening star, but they're both the planet Venus. It's not a star actually at all. But you have 3 objects there, 3 labels, 1 actual thing, okay? So you have to get the reference correct so that when you point at that thing and say, what is that? And someone can say, well, it's the morning star at one time of day. They can say it's the evening star at another time of day. Or you could say Venus at any time of day. All of those could have the same correct truth value. Now, how this gets implemented then is the catalog integrates with the consumer via a knowledge graph. And what we do is we add some machine learning. And the reason we add machine learning to this is that building ontologies is incredibly hard. It takes a long time, and you need a lot of special skill sets to do it. So normally, what we like to do is use some semi-automation to help pull those schemas off the data, to help align things. You can actually read against data sources and sometimes figure out quite well what's inside there, and then auto-align it to an ontology model. Okay, you can also even expand on ontologies as needed. We're working on this technology right now. It's quite exciting stuff. What it does is it reduces the barrier to entry to using these kinds of things. So what happens then is you get your catalog, and if you want to look up something like, I want to look up a chromatography study, and I want by some creator, be it a machine or a person, then what happens is it knows that the chromatography piece lives in a methods part, and it knows that that creator, that ABC123 ID, is a person. Okay, so it might be one of your scientists, right? So what's happening is on the left-hand side, you have an extreme amount of nicely confined, nicely described data, right? That you're able to then look up things in classes. And as we build off of that, so people, what I'm going to show later, people can be used for lots of things. People are in your HR system, people are work in your laboratories, people are your customers, people are your providers, okay? They can have lots and lots of roles, in other words. So you can think about people in a lot of ways. But here comes the problem. This is the nut that semantics has not been able to crack for a long time. It's the metadata versus instance data problem. So ontologies are very nice. Taxonomies are very nice. Controlled vocabularies are very nice. They all build off of one another, and they give you a great way to describe data, especially at the metadata level. The problem is, as we all know, and I'm saying this as a card-carrying ontologist who's been working in this longer than most people, is that they simply don't scale, okay? If you have to put all of that instance data in anyone's graph, you wind up in billions to trillions of nodes and relationships very quickly. And graphs are simply slow to compute over. I talked one time with one of the C-level guys at eBay, and he told me graphs were completely strictly forbidden from anything in their architecture. They didn't do graphs. He just said they don't scale. It's too slow. It has to be tables. So the problem, though, is if you just use tabular data, it's kind of dumb, right? The schemas in our relational systems, especially a lot of the legacy ones we have, aren't very explicit. They don't say a lot about the data. So how do we fix this? Well, the answer is what we need to do is we need to use the metadata to look things up, like the card catalog in the library. If you think about the card catalog in the library, it's significantly smaller than actually all the books, especially all the words and sentences and topics in the books in the library. So you have a many-to-one relationship, right? The card catalog, again, is like a fair data principle. It tells you where to go find the book. It tells you how to access the book, right? It might give you some interoperability if you're using an electronic one, so you can look up maybe by a genre or by an author or something like this, right? So you have certain connectivity, and of course you can reuse the card catalog over and over. So the common big data fallacy then is, let's move away from semantics then. Let's just talk about big data. And so there's a common hypothesis. If I have more data at my fingertips, then of course I'll have more answers. Well, actually, no. The major hurdle is that real-world data is very messy, it's inconsistent, it's biased usually, and it's noisy, right? So you need a new approach to big data, because just saying if I have more data is not going to help. You have to think about the kinds of data that you have. So if you think about the initial 4 V's of big data, you have the volume, velocity, variety, and veracity. The first 2, I'm not going to spend any time really talking about. A majority of the big data companies out there, the big box people, the Amazons, the Netflixes, the Googles, they're solving this problem. right? We don't really have a problem anymore about having enough space. Space is nearly limitless now. So you can have a lot of data, huge volumes, and people are getting very, very good at moving it around, especially in cloud architectures. Where we see people really stumbling a lot is on the right side of this. The first one is the variety. This is going to keep going up. There's new data sources out there now, customers coming to me with things like sentiment analysis. What do people say about our products? That didn't exist 10 years ago, really, right? Natural language processing technology, 90% of our data that exists is in an unstructured format. So that has to somehow be brought into, be made an asset inside of a company. So you need some nice pipelining, you need to have entity tagging, you need to maybe do parts of speech analysis and so on. And then you want to put predictors on those kinds of things so that you can say, what do I think is going to happen? We did some work in vaccines on this, for example, with flu vaccines, what we thought would be a predictor for the change that could occur. So the variety of data we see is growing, and it's not going to stop. In 5 years, there'll be all kinds of new data sources. And here's the problem. You can't throw the old stuff out, especially not in pharma, right? It's not like NoSQL means just throw all of your relational databases in the trash. That doesn't happen. You keep them, and you keep all your old file stores. So you keep all the legacy stuff, you just keep adding new stuff to it. The last thing is you have the veracity issue, and this is where you have to start adding things like mathematics. So this is actually where machine learning and de-identification, inexact graph matching, these kinds of things can occur, because now what you have to do is you have to provide these kinds of techniques to perhaps cluster the data, to perhaps understand the data. So the veracity has to do with the uncertainty in your data. My team and I, a bunch of us come out of the military and defense space from the past. So I worked in counterintelligence areas. And in that area, I can tell you the veracity was a big problem. A lot of people have 9 aliases, and you don't really know who's in this group or that group, and you don't know who is responsible for certain events, and you get a lot of bad data. So people are purposefully trying to trick you a lot of the time. So the veracity of data can be really hard to overcome, especially in science as well then. There's an analog there, because a lot of the data that you capture in your companies, everyone assumes is true. You assume it's correct, you assume it's accurate. It sometimes isn't, right? So you have to be able to know these kinds of things. So what we're working on is really helping people to figure out what is in their data and helping them link together these various kinds of data, the variety. So semantics plays one part, and statistics and machine learning and such play another part. So how does this come together? What do we mean then by a path to AI in terms of this? If you think about AI, there's a bunch of ways to think about it. I'm a philosopher by training, so I'm going to talk a little bit philosophical here. So John Searle, the famous American philosopher, talks about weak versus strong AI. Strong AI, he says, is AI that replaces people. It's completely intelligent machines. It's things that take over, that act just like you, where I don't need people very much anymore. We'll have these, fully autonomous robots, something like this. Searle says, of course, this is an old concept, but he says that's a really long way off. That's not the way that most people actually think of AI. Most people think of AI in terms of weak AI. Weak AI are tools. Weak AI is the idea that you have extensions. Think of it like a mental prosthetic, right? It's something that you use to do your job better, faster, with more accuracy or whatever. It's not replacing you, it's augmenting you. So, of course, there's a huge role of statistics to play in all of this. You have neural networks, you have machine learning, you have deep learning now. Deep learning is especially, I'll show in a moment, becoming extremely powerful for object recognition. The missing link in most people's discussion of AI is semantics. It's the meaning. What does the stuff mean that you're looking at? I know a lot of people who can do a lot of fancy things with statistics. The problem is they don't know what they're actually saying or what they're looking at, or they simply can use statistics to say anything, right? There's an old saying that says, all liars can use statistics and all statistics can be used to lie, right? You can take statistics. If I ask a question, so statistically speaking, what do you think is the most dangerous place in the world? The place you would face the most danger, chance of being stabbed or robbed or anything. Does anyone have an idea? What do you think is the most dangerous place in the world? Anyone? Yes, what? No one has any idea? How about if I told you it's Vatican City? Why would it be Vatican City? Should be somewhere, in a war zone or something, right? Or it should be in a It's because statistically, anything that happens in Vatican City, the population's so tiny that significant portions of the population are always affected by these bad things, right? So there's this interesting book that some German guys wrote. I shared a stage with them at a different conference, and they were able to show that using statistics, they could show all of these things, like it's actually better to not wear a helmet riding your bicycle than it is to wear a helmet. They showed that the Vatican was the most dangerous place in the world to be, and so on, right? All using statistics. And their whole point in this book is be careful of statistics. In fact, I believe that was the name of the book, is something like Achtung Statistik or something like this, right? The missing link is the semantics piece. This is where a lot of people get the machine learning and the AI part wrong. If you don't know what you're talking about, and if you can't make associative kinds of relationships, then you're not going to build machines that are going to augment us very well. They're not going to look and act and be very natural to use. So what we do at Ostus, and I'm going to show you this with our new product leap analysis, we bring statistics and semantics together, okay? It's like the Principia Mathematica. Russell and Whitehead wrote this book that talked about what are the foundations of logic and mathematics and where do they join. And so we took this very seriously and thought, what if we applied that same type of idea? What if we applied this philosophy to software development? Well, what you start to see then is if you start looking now at machine learning and deep learning on something like image data, you can actually start to see now that the machines are, in fact, getting better. In fact, the machines are now better than people are. And why is that? Well, because back in 2012, they switched the algorithm to a deep learning approach called AlexNet. And what happened at that point was that was where the really tremendous capabilities came from that allowed them now to say, machines can outperform humans. Humans still operate in a 5 to 10% error rate when looking at objects. They have this latest algorithm developed in 2017 that's up here, this SENet, runs at somewhere around 2 to 3% error, okay? And the reason is because the variety and the veracity in this case are really driving these kinds of new innovations. And more data is now actually better because you have to train these things. That's both a plus and a minus. So if you don't have a lot of data, if you're in a fairly data-starved environment, it's very hard to train these things up. You have to manually then basically build gold standards and things. So we call this concept of bringing the statistics and the semantics together to drive this kind of AI, we call it big analysis. And we have a website, we bought the domain name. So if you go to www.biganalysis.com, you'll see me and some of my team. And this is what we've done, is we said, look, you need to take the statistical and the machine learning part and you need to combine it with the meaning part, with the semantics part. And you have to be serious about this. And so with big analysis, what we say is, look, what if we then start to approach our data, like I said before, as Internet of Things devices, and we think about this differently. What if we stop for a moment building data warehouses and data lakes? What if we stop bringing all the data together for 1 minute, and instead we think about something like virtualization and federation? So a data warehouse is a great proven technology, but the problem is it works pretty much mostly on structured data. It works more on legacy stuff. It's not very strong at doing NLP work. It's not very strong with image or any of these things. So people said, okay, well, let's go to lakes. Data lakes, though, are like this one closet in your house. If I told you you have to put all of your items in your house in one closet, that's a data lake. Your food goes in there, your clothes, your cat, your golf clubs, everything goes in this one closet. And then you want to go bowling, and you realize you have to go dig through everything you own to find your bowling ball, and you think, I'll just go buy a new one, right? I don't need to do this. And that's what people are doing with their data lakes. There's so much stuff in the data lake that they can't even find what's in there. So guess what? My customers just go run the experiment again. I know people who've ran experiments 6, 7, 8 times in a row simply because they couldn't go find the data that they needed from the ones that were done in the past. This happens a lot. So if we now challenge this model and we start to think about the disconnection of all your things, you have instrument data, you have your existing operational databases, you have semi-structured data, you have documents, you have semantics, you have the whole open source community. You put this lightweight semantic layer in the form of this catalog on it. You combine that with your data science, which means your machine learning, your text analytics, your statistical items, and this allows you to drive up to analytical tools, to visualizations, and to reporting. And I'm going to show you now the future. We're going to run this tomorrow in the workshop. If anyone wants to come and see it, we'll be showing it live, running in an Amazon cloud. It's a new product we've built called Leap Analysis. It basically takes all of the things I just talked about and puts it into a pretty simple to use tool. Why? I want to build virtual data lakes. That's the key. I want to speed up the process, and I want to drive it with semantics. A core problem today is that the preparation and the integration that's needed to build a data lake is way too high. It's far too costly and it's far too time consuming. So if you're going to start copying and migrating data, good luck. The problem you wind up with is you have the original copy of the data, and then you make another copy and you put it into some system, and then you have another system that sits next to that one, so you put a copy of the data in that system, and on and on and on. So one of my customers, I flat out asked them this in one of the workshops we were doing. We were talking about architecture, and I said, hold on a minute, guys. Do you realize what you're saying? You've already said you're going to have the original data, a copy of it in this tool, and a copy of it in this tool. And what happens when you get the next tool and the next tool? How many copies of your data do you want? You have to store all of that stuff, but more importantly, you have to maintain it. You have to maintain the connection, because things will change over time. Data lakes face major obstacles for implementation, like I already talked about, and the big problem with data lakes, and I don't care who you are, it's indexing. If you don't index properly on a data lake, then you can't find the stuff that's in the closet. And indices are really hard to build because they're built by your IT people. They're not normally built by your subject matter experts. So when your scientists want to go look up something new on CRISPR, and CRISPR is not connected inside of your data lake, good luck. So the integration then becomes really difficult. So I have a clear message for everyone. Stop. Embrace your data silos. Stop trying to bring everything together, right? I'm saying the exact opposite of practically everyone else in the world. So instead of bringing everything together, instead of building that one big super warehouse that you're going to hold all of your stuff in, just leave your data where it is. That's what your IT people want anyway. People don't like to give up control. They aren't going to give up the databases. They're not going to give it up to you. They're not going to make copies. This is a fallacy. This is exactly what we've said from the semantics community now for over 15 years. It's never happened. No one puts the data together. So we have a very simple slogan: embrace it, live with it. Instead, what we've done is we've built an engine that can sit on top of fully federated, fully disconnected data sources and can speak semantics to it via knowledge graph. So in other words, it's an API connector with a very, very sophisticated set of translators that allows you to Sparkle query a knowledge graph, and it talks to any data source. We can connect these things in a matter of minutes to hours. Because we do the machine learning and we pull the schema, you can see the schema in the tool, and simply we can have some automation that can even align concepts to the knowledge graph, and other things if you're unsure of it. You sit down with the subject matter expert for 10 minutes and say, what is that column, what is that column, what is that column? Oh, that's temperature, that's pressure, that's some ID of an instrument. So the main topics: companies have to speed up the process of integrating data. I've been on too many projects where we spent a year and very little got integrated. I heard a talk by someone from GSK that floored me. They said that they integrated pretty much point to point in a cloud, 1,000 databases in their R&D department. It took them roughly 3 years and somewhere around $10 million plus. I thought, wow, okay, I don't have many customers that would give me that kind of money, and I'll see them in 3 years, and I'll have half your data connected, right? So that was an eye-opener for me. Just saying semantics, just saying make your data smart. So everyone's selling now smart data lakes and smart this and smart that. It's a nice phrase to put on things. Usually if you hear the word smart, what I want you to think of is replace it with the word slow. Because if you're going to put the instance data into graph and make it smart this way, you're pretty much going to slow things down. And as I said, the world is really moving to decentralization. So virtualization, federation, using these things for complex problem solving and having pattern and model reuse is key. And I'm hearing this all over the place now. So this is kind of what it looks like when someone uses our tool. This is actually a use case, and I can say where this comes from because they don't care, we have an agreement. So AstraZeneca has been using leap analysis now in some pilot projects since last year. They are pleased with the results. This was a kind of an eye-opener for them because what we did is we were able to basically say a user goes in, can write a query. The query goes against the model. That's the subject domain. So the subject domain we have loaded in there a person ontology. What they were able to do is we pull and align CSV file system and a relational system that had a bunch of their data in it, peptide data. So what they wanted to do is they wanted to look at these data sources and then go outside and compare the proteomics data that they had to what existed in Nextprot, which is an open source triple store that they don't control or own. So what we do is we write one query against the model. It queries all three of those data sources. That model lives here in an internal triple store. Only metadata though, no instance data. So the graphs stay very small and fast. You see there's an alignment store that holds the arrows. That's basically holding your mappings. That's in a MongoDB, so it can scale very big. Now, if you want to cache results, you see the query response comes back, and what it does is it tells you here where the data came from. So you'll see if it came from your CSV store, you'll see if it came from your SQL store, you'll see if it came from your Mongo, you'll see if it came from wherever. And so now what happens is you can either cache that result or you can blow it away. So I'm talking to people in the financial sector. They want to do this for CRM data. They want to use third-party customer data, but they don't want to keep anything. GDPR, another one. I'm talking with another company who now they can look at who's using, watching what entertainment on a flight, but they don't have to store the individual data of who you are and get your permission and stuff. They just know that whoever was in seat 32G watched 3 Disney films and 1 sports thing, right? So that's what they want to know. They want to know what to put in and out of rotation, but they don't want to keep the instance data. In this case, the instance data stays where it is. All your security stays down there. You don't have copies of data going into a new system. You don't have instance data getting pushed into a triple store or a graph. And you don't have this problem of GDPR and having all this instance data about people, because all you're storing is metadata. So if you're interested in seeing this, again, we'll be showing it tomorrow in the workshop. Thank you very much for your attention. I hope I was able to keep everyone awake after lunch. It's always a tough gig. I think Michael riled everyone up. So anyway, thanks very much, and we'll be here if you want to chat about any of this. Thanks.
There is one point, actually. I mean, you are talking about using the data, right? But then you mentioned cleaning the data, right? I mean, this is a huge advantage of using this type of technology because this is simplifying in the end, right? And then making things even easier when you do data visualization and reporting, right? Can you elaborate a bit on that? Because
correct. So just to be clear, I'm not in the business. One of the best questions I had asked of me was I was on a call, I was demoing this product, and somebody said, yeah, cool, I get it. Okay, I get what you are. Tell me what you're not. And that stopped me for a minute, right? But then when I thought about it, I said, okay, that's a good question. We're not an ontology editor. We're not a reference data manager. And I'm not a data cleansing device, right? We glue things together quickly for people so that you can take a look what's in there first before you commit to pumping it into your data lake. A lot of people are pumping things into their data lake that's dirty and that they don't even know if there's any value to having it, right? But they shove it all in there first and then they go clean it up after. This at least allows you, when it comes back, you may say, ugh, this data is full of duplicates, or this data has a really bad schema around it, right? But it allows you to see that. Now if you want to go in and go to that data owner and say, please clean this up, you've targeted the areas to start with. That's what I'm trying to get my customers to. I'm trying to get my customers to a point to say, look, before you make this big investment, before you spend a year cleaning data that no one's going to look at, why don't you see if there's even any value in there first? So when we're talking to people about this, one use case that came up, in fact, I think Peter will attest to this, right? We were talking with a large hospital system about if they could use this to look across patient data, because it exists in, they've got thousands of studies in all these different systems, but it's really hard, it's impossible actually to physically put that data together because of all kinds of rules and regulations, and it's in all these different systems and so on, but they'd like to have a view on it. So yeah, the idea is to get you up and running, looking at your data, figuring out what you have, figuring out what needs to be cleaned, and figuring out whether that thing is something you should move into your lake or your warehouse or not. And that's why another thing that we are not trying to be the world's fastest query engine, okay? I can only run on how fast the things are that I'm running against. So that next prod triple store, that example I showed you, it takes 1.5 to 2 minutes for that query to run, because it has to do a graph scan to look for if I ask it for an exact gene name, it has to scan that whole graph. And that graph is an open source triple store. I can't control how fast that triple store is. If you want to make it faster, pull a copy in and do something, do some kind of, computational wizardry on it. But what I will say is one of the coolest things we did is we've already built a query optimizer into the engine. So now, using AI type things, the first time it runs the query is the slowest. Every time it runs these queries afterwards, it optimizes, it figures things out. And we can also get very fancy with what we cache, right? So in these cases, again, I'm not trying to be the world's lightning fast query engine. Somebody said, well, how fast is it, how fast would it be to run across 50 disconnected data sources? I said, how fast is it to put those 50 disconnected data sources in your data lake, right? How fast is it to build a data lake? It takes a long time. Right? So if your query takes 6 minutes, if your query takes an hour, if your query takes half a day, at least you get the answer, right? That's the key. We're looking for accuracy. And then we can always work on performance, because we've already cut this thing orders of magnitude like this, right? I never worry about computer scientists making things faster. What I worry about is the answer right? That's usually the hard part. So anyway, thanks very much. And like I said, we'll be here. Oh, yes? Hold on. Question?
Eric, that's very interesting. I have one more question. Can you give us an idea about the efforts you had to do when implementing this concept at AstraZeneca in terms of time and how many people you had to work on that concept?
Yeah, so on the customer side, let's see, we had the data owner, we had a subject matter expert, we had their project manager. We were already we're on another project with them building a data catalog, okay? And what happened was I saw one of the sources that they were connecting, it had been months. I mean, it was over a year still mapping all these things. And I said, look, there's got to be a better way. You can't take this long for all these different data sources. You have too many. So I said to them, we built this thing. The proof of concept we ran initially was 3 months. We ran another proof of concept in oncology with them as well, which was shorter. It was a matter of maybe 6 to 8 weeks. But what we're doing now, in fact, is since the engine is now more in place, the engine is more sophisticated. We officially launched last month, March 19th, at Enterprise Data World in Boston. So it's a real product. It's not some idea. But what we're doing now is we're going to customers and we're saying, look, bring a few of your data sources in and we'll hook you up in 3 to 5 days. Then we'll leave it with you for 60 days to play with, write some queries, we'll leave you a cheat sheet on how to do Sparkle, so you can figure that. The Sparkle language, by the way, is going to go away eventually. We need to get to smart forms, we need to get to pictures you can draw, these kinds of things. But for right now, you have to still write Sparkle queries. So we show people how to write the Sparkle queries, they bring the data, we go through use cases with them, we talk about the foundations of the technology, how it works. We plot their use cases so that they have a roadmap, so that they can plan projects and things out around this. And then we spend between 1 to 3 days just hooking everything up for them and getting it to work, writing some queries and so on. We leave it behind, you get it in a cloud instance of what you're choosing. Right now we use Amazon. And then they can play with it. They can show their management. They can decide if this is something they like. And if they like it, then they can buy one. We sell it basically as the base engine. You buy the connector types that you want. So, if you don't want a connector for NoSQL, that's fine. You can start with just relational or relational and file store or whatever. And then we look at the compute environment it's going to be in. So how many cores, how much memory is on the server that it's going to sit on. So in that sense, yeah, I mean, basically we could get you going in about a week. And you could have something live that you could be running, showing people, and figuring out if that works for you.
Great. Thank you very much.
Thanks.